Hello everyone, welcome to our first in-person theory lunch of this semester. We have our own Ainesh to talk about the new low-rank approximation result.
Okay, thanks, Praneeth, and thanks everyone for coming for the talk. And it's really nice to be giving this talk in person back at Theory Lunch. So today I'll be talking about low-rank approximation in the matrix vector product model, and I'll define exactly what that means. But feel free to stop me at any time and ask questions. And I should mention this is joint work with Ken Clarkson from IBM and David Woodruff, who is one of my advisors here at CMU. And this work is to appear at Stock this summer. And the paper the talk is based on is available on arXiv. Okay, so let me get started by defining the low rank.
Back to that slide for a second. I need to write the title. Okay, thank you.
Okay, so let me start by defining the low rank approximation problem at first intuitively. So here we're given a matrix A. Let's say this is a matrix with real entries. It's an n by d matrix. And in addition, we're given an integer k between 1 and d. And the goal is to take this matrix A and factor it into two matrices, x and y, such that the inner dimension of x and y is k. And we also want that the product of x and y is close to A in some natural sense. Okay, but in this talk, we'll ask for a bit more structure from the factorization. These problems tend to be equivalent, but the exact formulation that I want here is that I don't want an arbitrary factorization. I want a factorization where the factor looks like U transpose, where U is a D by K matrix. And in addition to being a D by K matrix, this matrix U will have special structure. It's going to be a projection matrix. And I'll define what that is. But intuitively, you should think of this as a map that takes vectors in D dimensions and maps them to vectors in K dimensions. So you want to map your vectors to a low dimension subspace. The vectors that will be of interest will be the rows of A. So the operation that U transpose is doing is taking each row of A and mapping it to a lower dimensional subspace. And we want the resulting matrix. So if we compute the product of U times U transpose times A, we'll get a rank K matrix, and we want this rank K matrix to be close to A. And I'll make precise in what sense in just a bit. Okay, so let me give you a picture to keep in mind for what this projection matrix is actually doing. So we can write the problem here as like the following optimization program, where we're minimizing over all D by K matrices, such that U transpose is actually a projection matrix. And what this projection matrix is doing is it's taking, let's say, the first row of A, let's call it A1, and projecting it onto the column span of U. So in this example, the column span of U is this one-dimensional vector. A row of A is this two-dimensional vector that's denoted over here. And what this projection matrix does is just finds the orthogonal projection of A onto the span of the columns of U. Okay, and we want to minimize over all such projection matrices.
The column span of U, it's a certain linear subspace. What dimension is it?
Right, so if U has K columns, it's going to be a K dimensional subspace of RD. And in this example, you will have one column, in which case, in this 2D example, it's like a line.
Okay.
Okay, any other questions?
And you're projecting
Each of the rows of A.
Each of the rows of A, A1, A2, etc., onto that.
That's right.
Same
subspace.
Same subspace.
And what you want to find is the best subspace, in the sense that once you project each row of A onto the subspace, the resulting points are close to A in some notion of closeness. And I'll define what this notion is, but for now, you can think of it as your favorite matrix norm.
And the distance? The distance is that measure of the distance to A. Okay.
That's right. For now, you can think of it as Euclidean distance.
Could this be thought about in terms of a linear, if you have just the points in two dimensions, you want to find a line closest to those somehow?
No, so this is not regression. So that problem would be like fitting a line through a set of points.
It's not like
No, because like what you're trying to do is find a low dimensional embedding of the points where, if you look at projecting the points along that dimension, basically, it's going to be like, okay, so let's say you start off with 10 dimensions. And what you want to do is find a two-dimensional projection where, you still have this property that after you project the points into two dimensions, you're still, close to the original points in some, it's a Euclidean distance.
That's kind of like it.
I'll show you an example that will make it clear. Yeah.
Is this equivalent with like the regular low-rank approximation?
That's right. This is equivalent. From here, you can extract like two factors. Like one factor will be AU, and the other factor will be U transpose, and then you'll get this n by k by n kind of factorization. Good question. Any other questions? Okay, so let me just make this notion of projection matrix formal. A matrix P is going to be a projection matrix if it can be factored into the matrices U transpose, where U has k orthonormal columns. Okay, and let's just recall what it means to be have orthonormal columns. It just means that each vector is a unit vector, and all pairwise inner products are 0. So the columns of U are unit vectors, and if you take the inner product between any distinct columns, it's going to be 0. So it's essentially a basis for the subspace spanned by the columns. Okay, so such a matrix is a projection matrix, and what we want to do is optimize this objective over all rank K projection matrices. Note that we can concisely encode this constraint by writing U transpose equals the identity, the k-dimensional identity. And the reason for this is like, if you consider the diagonal of this matrix, it's going to be all ones. So the inner product of each column with itself is going to be 1. And every off-diagonal entry in this matrix is going to be 0. So the inner product of any two distinct columns will be 0. Okay. So we get this optimization problem, which completely captures the problem that I started out with. And we would, for the rest of the talk, we would like to see how to come up with algorithms to efficiently solve this optimization problem.
This is a naive question, but that type of absolute value, does that mean the difference, the square root of the sum of the squares of the?
Great question. So let me define it. So this norm is going to be a matrix norm. So these two objects are matrices, and we're taking the difference of them. The resulting object is still a matrix. And the norms that we care about are like Frobenius norm or operator norm or nuclear norm. So for now, let's just focus on Frobenius norm. This is saying you want to minimize the sum of squares of the entries. Okay. And we'll also be interested in other norms. I'll define them. Maybe you've heard of them, like the operator norm and nuclear norm. And we'll get to their precise definition in a bit.
So what if k equals n minus 1? It's almost as big. When k equals n, then you can get it exact.
That's right.
Right, but what if it's n minus 1?
Right.
How close to the diagonal can you get? Can you get like things that are off by 1 from the diagonal or something?
No,
Diagonal matrix or what?
no. So you can be arbitrarily far off. Actually, like the resulting matrix will not have some nice structure always. Like you can cook up instances where the resulting matrix doesn't look tri-diagonal, for instance. But I'll characterize exactly what the optimal value looks like to this optimization problem in just a bit.
Okay.
Yeah. Any other questions about the problem setup? This is the entire problem setup. Okay, let me then move on to a motivating example for why you would want to solve such a problem. And one canonical example is to use low-rank approximation to detect structure in data. So for instance, you could start off with a point set and think of this point set in really large dimensions. But for our example, it's just going to be 200 points in 3 dimensions. This is like a toy example. And we can write this point set as a matrix A, which has, n, like 200 rows and 3 columns. So we've placed our points in this matrix. And what we want to compute is the best rank 2 projection, as I defined in the previous slide, for the set of points that we see here. And the norm that we want to minimize is the Frobenius norm, which is the sum of squares of the entries. So if we do this and we find the optimal U, and project each point that we started out with in 3 dimensions to the resulting point. Oh, this is not very clear, but essentially the image here is that you get a set of points that lie in a 2-dimensional subspace of R3. And the guarantee that you have with these points is that they minimize the pairwise, like each point to its corresponding image in R3, the Euclidean distance is minimized. So in that sense, this is not really like fitting a line, but you're doing something more high dimensional.
Is this k equals 2?
Yes, this is k equals 2. Okay, and this problem is used as a subroutine, like low-rank approximation is used as a subroutine in big data analysis. It's used even in designing algorithms for learning mixtures of Gaussians and so on. So it has a lot of applications. Okay. So now let's get to the interesting question. How do we solve this optimization problem? The first thing to observe is it's non-convex, so we can't use any simple algorithms like gradient descent to solve it. And in order to get to how to solving this, let me first tell you what the optimal value to this optimization problem is. And to do this, we'll use the singular value decomposition. So the singular value decomposition for any matrix A says that you can write this matrix as a product of 3 matrices, P, sigma, and Q transpose, where P will have orthonormal columns, sigma will be a diagonal matrix, and Q transpose will have orthonormal rows. Okay, and this is possible for any matrix A.
Are those squares?
Are the dimension?
No, sorry, A is not a square matrix.
A is not a square matrix. A is n by d. So this is going to be n by d. This is going to be d by d, and this is going to be d by d.
Okay, so those on the right are square matrices.
That's right. A bit more precisely, the matrix sigma on the diagonals has what is known as the singular values. These are non-negative numbers arranged in descending order. Okay, so how do we get a rank K matrix out of this? We'll do something fairly natural. We'll take all the top largest K singular values, keep them as it is, and truncate all the rest. This operation has the following effect. It ends up selecting the top K rows of Q transpose, since the others are getting multiplied by 0, and the left K columns of P.
If I find a solution that didn't have those diagonal elements sorted,
yeah,
could I just rewrite it by changing?
Right, it's just a permutation.
To make it that way?
That's right, it's just a permutation, right? Like you can arrange it and apply the permutation to the you have to apply the same permutation to the rows of P, rows of Q transpose and the columns of P.
Okay, thank you.
Sure. And the resulting matrix we'll denote by the P sub K, sigma sub K, and Q sub K transpose. This is the truncated matrix where I ended up picking, the top K rows of Q transpose and the left K columns of P. And now the optimal solution is actually given by setting U transpose to be equal to Q sub K transpose. So in other words, the optimal solution is picking the top K rows of this guy. Okay, and there's like a really nice theorem proved back in the 30s that this solution is optimal for any Schatten norm, which I haven't defined yet, but in particular, it's optimal for Frobenius norm, operator norm, nuclear norm, and so on. Okay, so this characterizes the optimal value of the problem. And now we'll see how to compute it. But any questions so far?
So the reason you're interested in this problem for different reasons than those guys in the 1930s, right?
That's right. We'll be interested in computational aspects of this problem. Like we will try to figure out how to actually find a good approximation to the solution really quickly without actually computing this singular value decomposition.
So why were they interested? Why did those mathematicians bother with this problem? You know?
Right. So these kind of questions show up in functional analysis and quantum mechanics and so on. And we'll see some of that later on. Like there are connections here, which is why they were interested in studying these operators basically and characterizing like optimal values of these operators. But I can't tell you exactly why they were interested. I suspect that's why. Okay. So let me define Schatten norms and the norms that I mentioned, like the Nuclear norm, the Frobenius norm, and Opper norm will be special cases of these. So let's recall the singular value decomposition. Now the Schatten norm is just to take the diagonal of the diagonal matrix, which is the singular values, and look at the LP norms of this matrix. So the Schatten P norm of A is going to be summing over the singular values to the pth power and taking the 1 over pth root. Okay, so think of the diagonal as a vector, take its LP norm, and you'll get Schatten norms of the matrix. Okay, for P equals 1, this is the nuclear norm. For P equals 2, it's like our favorite Frobenius norm, and P equals infinity, which selects the largest singular value, is the Opper norm. Okay, any questions about that? Okay, so let me summarize what we saw so far. We have this optimization problem, it's non-convex. We like to find this rank A projection matrix. The truncated singular value decomposition is the optimal solution to this problem. But unfortunately, computing the singular value requires n times d to the omega minus 1 time, where omega is the matrix multiplication constant. So for, let's say, a square matrix, this requires n to the omega time, which could be quite slow. And what we'll be interested in is to solve this optimization problem much more efficiently. Okay. Before I tell you how to get efficient algorithms, let me mention the model that we'll be working in. This model is like a nice abstraction for studying linear algebra problems, and it's called the matrix vector product model. And what you're given here is that you start off with a matrix A, and the way you access this matrix is via matrix vector products. So you're given this matrix A, you hook up some vector V1, and you get to see A times V1. And then based on this result, you can cook up another vector V2, and then you get to see A times V2. And these queries can be adaptive. And this is a well-studied model in numerical linear algebra. And the measure of complexity here is just the number of matrix vector products that you end up making. Okay, so we'll measure the complexity of our algorithms in terms of this quantity, the number of matrix vector products. Any questions about the model?
So you're saying that the output of your algorithm is not the matrix A.
No, the output is,
your algorithm is a way of doing those queries you just described.
the output is this matrix U, which is the projection.
Right. But that you're saying it's not the output.
No, I'm saying this is the output. The output will be a set of vectors, which will be the columns of U.
Okay, but then what does this have to do with the query model?
Right. So the way you get access to A is not that A is stored in RAM.
So you don't have to compute A.
That's right. So A could be implicit. So think of it as an oracle, right? You give this oracle a vector, and it'll tell you the matrix vector product with A and return you the resulting vector. So you're not allowed to read the matrix in some sense. Like the matrix is stored implicitly. There's an oracle, I give the oracle a vector, it returns me the matrix vector product. Like here.
Isn't A the input to this problem?
Yeah, A is the input, but the way you're accessing the input is by this matrix vector model. I mean, in other words, like the complexity that we care about is going to be the number of matrix vector products that we make.
I see. To compute the final answer, U.
Yes.
You're going to be doing it counting the complexity in that model.
Precisely. And I'll show you an example of what this means in just a bit.
We have a few questions in the chat.
What are they? Oh, I can look at them. How important is the assumption of query adaptivity? Well, it's a model that I'm defining, so I'd like to define the most general model possible, which allows for adaptive queries. If you wanted, could you take dot products with E1, E2, etc., and still get? That's right. You can actually recover the entries of the matrix by querying the right vector, but this is gonna incur, like, if the matrix is n by n, this is going to incur n squared queries. And what we'll be interested in is minimizing the number of queries. And of course, this matrix vector product model can be implemented in RAM, right? Like you can read the whole matrix and like explicitly compute the matrix vector product. So It's just a cleaner way to understand algorithms. Does that answer all the questions? No. A is an n by n matrix. So if you want to get each entry precisely, you would have to do n squared queries.
You can query coordinate. You can get the first column.
Oh, sure. That's true. Yes, n queries. Thanks. Okay, so let's consider like what would be the first natural algorithm to try to solve this problem. Our model is pretty limited. Like we start off with a vector and we can do matrix vector model products. So the first algorithm to try would be something like power method. And what power method does is it starts off with a random vector g. It computes a times g, and then repeats, like it applies a to the resulting product and so on, and does this t times. To understand how well it does, we're going to look at a simplification of the problem, where we're instead of the general problem with k being arbitrary, we're going to fix k to be 1, and we're going to fix the norm to be the Frobenius norm. So now we're just optimizing over unit vectors. We want to minimize this difference over all possible unit vectors. Okay, and power method gives you a natural algorithm for this. You just iterate t times, and you set the result, you normalize the resulting vector, and you say, this is my approximation to my solution. Okay, so hopefully this makes the problem and the way we're solving it at least a bit more intuitive. This is how you access the input. You count the number of matrix vector products. In this example, it's going to be t. You get one vector at the end, you normalize it, and you output this as a solution. Any questions? Yes.
Why is this an intuitive thing to do?
Well, our model is fairly limited, right? Like we're given access to this matrix in like this matrix vector product sense. If you do this iteration, you would expect that the resulting vector that you get is closely aligned to the top singular vector of A. And that's what characterizes the solution, if you remember the optimal solution. So the hope is that if you do this iteration enough times, the resulting vector will be like close to the singular vector, the largest singular vector of A. Okay, so let me say a bit about.
Well, where's you in that then? Well, how do you get you out of that? Oh, U's there.
So this is the approximation to U. This is the vector I'll apply.
Okay. Thank you.
Okay, so this is just writing the same algorithm out a bit more formally. But let me tell you how well this algorithm works. So there might be other citations for this, but the one I know is this nice paper by Musko and Musko from 2015, which says, if you run this power method algorithm 1 over epsilon times up to log factors, then the resulting vector u tilde that you get is going to be a 1 plus epsilon approximation, relative error, to the optimal cost. Yes?
Sorry, just a quick question to clarify. So the reason you're doing the power method is because you're trying to approximate the largest singular value vector. Yes, to be the largest, I don't forget what it's called.
Right.
And when you do this power method thing, this is how you compute.
This is one algorithm to compute the largest. Yes. So yeah, what we actually want to do is get a good approximation to this objective. And the claim here is that if you do power method 1 over epsilon times, you get a 1 plus epsilon approximation to opt in this objective sense. Okay, I'm not going to prove this theorem, but that's not the main point of the talk. But it's to set up some context for these results.
Can I see where you get U from the power method again? That last equation.
Sure. Sure. The picture is this: like you start off with a random vector g, you iterate it a bunch of times. This corresponds to the vector that you get after applying a t times is a to the t times g.
So G, what is the dimension of G?
G,
let's 1 by something vector? No.
Yeah, it's going to be a column vector. A is, let's say, n by n. In this example, it's like a square matrix, and G is an n-dimensional vector.
ATG, what is the dimension of ATG?
It's still n. Every time I'm multiplying an n-dimensional vector by an n by n matrix.
thought U was K by N.
Nope. K is 1. U was N by K.
K is 1, I'm sorry. I didn't see that K was 1, you have the right corner.
Right.
Okay. So you're just solving the one problem.
The one-dimensional problem, yeah.
This is baby stuff.
Yes,
compared to
yes.
What you really want to do.
Absolutely. This is just to build intuition. Yeah. I actually give you some algorithm. Okay. Are there any other questions? Okay, let me. So what this theorem claims is that if you set t to be 1 over epsilon for your desired accuracy parameter epsilon, then you get a resulting vector, which is. How do you choose G? Yeah, G is just a sample from N0 identity. It's just the n-dimensional constant with covariance identity. Yes, I'm going to ignore probability statements here. Good question. Okay, so how do we do better than this 1 over epsilon? The key idea here is this thing called a Krylov subspace. And what is a Krylov subspace? So the idea here is that instead of just looking at the last vector, you keep track of each intermediate vector that you had. So in our power method iteration, we had G, then AG, then A square G, and so on. But we were only outputting this last vector, right? But what we could hope to do is keep track of all these vectors, compile them into a matrix by joining them together, and find the best vector in the column span of this matrix K. Okay, so this matrix is known, the column span of this matrix is known as the Krylov subspace. And the Krylov methods have the following idea. They say find the best vector in this Krylov subspace.
Is there a capital K or something? Is that
Yeah, it's a capital K. Stands for Krylov.
Not to be confused with the lowercase k.
Which we got rid of. For now, we'll be thinking of the rank 1 case.
We're still in the rank, rank 1 case.
That's right. That's right. I'm going to just show you how to solve the problem for k equals 1 just to begin with. Okay, so what do we know about this method? The same paper has this really nice result that if you study Krylov methods, if you actually find the best vector in the subspace and you output that vector, then you only need 1 over square root epsilon iterations. So we get this square root factor saving. And the guarantee is still the same. It's going to be a 1 plus epsilon approximation to opt. Okay, and let me say a bit about why you can do this and why you can implement this algorithm in the matrix vector model.
Anupam asks how you find this vector.
Great question, Anupam. Here's the answer. Here's the algorithm. So you start off with your Krylov subspace K. You compute an orthonormal basis for this Krylov subspace. Okay, so let this basis be the matrix Q. You compute then from this Q transpose A squared Q. Okay, so if the Krylov subspace has T columns, then this is going to be a T by T matrix. And then we'll just compute the top singular value or singular vector of this small T by T matrix and output U tilde to be Q times the first singular value. Okay, the precise nature of this algorithm is not too important. The point is that you can implement this algorithm in the matrix vector product model. And it only uses 1 over root epsilon matrix vector products. Yeah, we'll not be too concerned about the precise nature of the algorithm. Okay, but I will give you some intuition for why this beats power method. Like, why does it do better than 1 over epsilon? So essentially what power method is doing is it's computing a to the t times g, where t is the number of iterations. If you write a in its SVD, then essentially what it's doing is it's looking at each singular value and applying the function x to the t to each single value, and then multiplying it by a random Gaussian vector. Okay, this is what power method is doing in a nutshell. What Krylov methods try to do is approximate this function x to the t using low degree polynomials. In particular, what you can show is that there is a root t degree polynomial, the Chebyshev polynomial. The definition of Chebyshev polynomials is not important, but essentially what you can show is that you can approximate this function in some bounded interval with root t degree instead of t degree. So this gives you the square root t saving at a very high level. And you might have seen this idea before. This idea shows up in optimization and ML and all kinds of theoretical computer science, which gives you the square root saving. Okay, and let me make one more comment. the Chebyshev polynomials are the best approximation to this function, and this root t degree that you get here is tight. You can't hope to get an approximation which is better than this root t degree. Okay, so what does this mean? This means that instead of computing t iterations of the form a to the t times g, the best vector in the subspace can be found with a subspace of size root t. And this translates to the 1 over root epsilon guarantee instead of the 1 over epsilon guarantee.
Does this use some Chebyshev polynomials
Yes.
relate to other type, I mean, that's what they're used for, right? Even one-dimensional, are these one-dimensional polynomials, right? Chebyshev polynomials.
Mhm.
They're one variable.
That's right. We're applying it to the function x to the t, where x to the t is applied to each singular value of the matrix, right? So we'll just approximate each singular value, x to the t, by some Chebyshev polynomial.
So it gives you a way, the Chebyshev polynomials give you some way. It can be combined together to get
Right.
powers of t in more efficient ways.
Right, exactly. So essentially,
I've seen that before, like 30 years ago.
Right.
when I was studying numerical analysis.
right. This is a really old idea.
Yeah.
This shows up everywhere in numerical linear algebra, TCS, and stuff. Okay, so okay. Conjugate gradient. I gave you the algorithm, Anupam. It was on the previous slide, and for k equals 1, it is actually.
Chebyshev polynomials show up in conjugate.
Oh yes, they show up in conjugate gradients. Exactly. That's right. This is the idea in conjugate gradient. Absolutely. Okay, so let me go on to the central question that we are asking. So we saw an algorithm that gets O of 1 over root epsilon matrix vector products. Is this necessary, or can we do better to solve this problem? And the answer to this question is spoiled by the title of the talk. In particular, our main result is that 1 over epsilon to the 1/3, or 1 over cube root epsilon matrix vector products are necessary and sufficient. So that's the main result for this k equals 1 toy problem, where you're trying to find a single vector. Okay, so let me flesh this claim out a bit more. This is going to be a randomized algorithm. It's going to get the guarantee where you output u tilde, which is a 1 plus epsilon approximation to opt. You only use O tilde of 1 over cube root epsilon matrix vector products. And let me place this in more context by saying that we also show a lower bound, that if you want to solve this problem, you require 1 over cube root epsilon matrix vector products. So essentially, this 1 over cube root epsilon thing is tight, even though it seems a bit magical. Yeah, it's tied up to log factors. Okay, good. So this is the version of the result for k equals 1. So this here we are finding a single vector u, but we obtain a more general result. In fact, we obtain a result for arbitrary k and arbitrary Schatten P norms. So our result there is that it has the same flavor, but the dependence on k is linear, and the dependence on the Schatten P norm, the p in the Schatten P, is p to the 1/6. Yes.
Earlier you told us the optimal result is independent of p, right? Why does that algorithm depend on p? Can't you just pick because you're the bound at the end.
Okay, good. Yeah. So this is the formal result. The number of matrix vector products is k p to the 1/6 or epsilon to the 1/3. The kind of guarantee is over all rank k projection matrices, you find a 1 plus epsilon approximation to opt. In particular, for the special case of p equals 2, which was studied before by Moscow and Moscow, we improve on their bound, which is k over root epsilon. And we also improve over other bounds you obtain by sketching, which are like k over epsilon, for the special case of the Frobenius norm. For p between 1 and 2, there was only one previous result, and this is polynomially worse than both k and epsilon. Okay, For p larger than 2, this again improves on the one known result before, and this result actually requires number of matrix vector products that depend on the dimension of the matrix, whereas our result is like independent of n and d. So it really improves on this result. Yeah. No, I mean the lower bound is the one that we've proved in this result. Yeah. Okay, and finally, for the special case of spectral norm, which is like p equals infinity, we get a bound even for this case, even though naively you can't plug in p equals infinity as mentioned in this result. But if you set p to be log n over epsilon, you can recover this k over root epsilon bound. Yes.
I guess let me rephrase, like, for your first theorem, you have a theta, here you just have omega, like, so are your results tight here?
Good question. Good question. So our lower bound actually only holds for constant k and constant p. And that's right here. So we don't obtain any lower bound that grows with p and k. So we only obtain this 1 over epsilon to the 1/3 lower bound. And when p and k are a fixed constant, this is tight. But we don't obtain any results that grow with p and k, and this is a wonderful open question. That's right, just log d. It's like log squared d, I think. That's right. Good question. Actually, our algorithm is adaptive because it's doing this power method. Like you do one matrix vector product, you use it again in the next one, and so on. I have no idea what you would do if you restrict yourself to non-adaptive algorithms. But then that would be like really far from the right subspace, and you could probably show a lower bound. Yeah, maybe, but I haven't thought about it. Okay, any other questions? Okay, so let me tell you a bit about our algorithm, some overview of the proof, and I'll maybe mention the hard instance depending on how much time we have. Okay, so let me tell you the algorithm. So at a very high level, the main idea for algorithm is to optimize over 2 Krylov subspaces simultaneously. So let K1 be the Krylov subspace that we already saw before. Okay, here you start off with a single vector G, and you iterate this vector a bunch of times and multiplying it by A. Now the number of times we do this is 1 over epsilon to the 1/3. Okay, so this step takes 1 over epsilon to the 1/3 matrix vector products. This is the Krylov space that we saw before. This is the one that was used in the previous result. Okay, now we consider another Krylov space. Here, instead of starting with a single vector, we start off with a block matrix. Like this is going to be a matrix where each column of this matrix is going to be a random Gaussian vector. And the number of columns of this matrix is going to be epsilon to the 1/3, 1 over epsilon to the 1/3. And then we're going to power this matrix up a constant times, so log n times, let's say. Okay, so both these steps take O tilde of 1 over epsilon to the 1/3 matrix vector products, and they capture the 2 extremes that you could try to do in this Krylov subspace method. Right? You could start off with one vector, iterate a bunch of times, or you could start off with many vectors and iterate a few times.
And where's G come from?
G is again, I can just write it. G is again a set that is, each column is independently Gaussian.
Oh, so the same as G, the same as little g.
So it's the same as little g, but multiple copies of little g, and multiple independent copies of little g.
But so you're picking one of them and you're one G randomly.
Yes.
And you're running a whole bunch of iterations, 1 over epsilon to 1/3.
That's right.
And then you're also picking
in parallel.
a bunch of them.
In parallel.
In parallel,
yes.
Running them like log n times.
Precisely. Like just like log n times.
Okay.
And these are the 2 extremes that you could do with matrix vector products in this setting. Because your budget is like, at the end of the day, it's just this much. So you can start off with a lot of vectors, iterate them a few times, or you can start off with one vector and iterate it a bunch of times.
You're gonna do both.
And we're going to do both, and we're going to pick the best. So we're going to pick the best vector that you found from K1. Let's say it's U tilde 1. We're going to pick the best vector that we found from U2, from K2, call it U tilde 2. This is the algorithm that I showed before. And then we're just going to pick whichever one has larger norm with A. Okay, so what's good to keep in mind is that this whole algorithm actually only uses O tilde of 1 over epsilon to the 1/3 matrix vector products. Okay, and the main claim that we show is that this U tilde is going to be a 1 plus epsilon approximation to opt. So this is our entire algorithm for the special case of k equals 1. And I'm not hiding anything. Okay. So let me tell you a bit about how we analyze this algorithm. The first step that we need is this thing called a gap independent bound. And this bound is implicit in the work of Musker and Muskow. So what does this bound say? It says if I take the optimal solution after running t iterations of just plug Krylov of the algorithm that I showed you before, this Krylov method, then if I look at A tilde, A times U tilde, the L2 norm squared of this guy, this is going to be an additive 1 over t squared times sigma 2 approximation to the top singular value. Okay, so let me break that down a bit. So this is always upper bounded by the top singular value of A. And additionally, what we say is it's lower bounded by this additive term, which if we run for t iterations is 1 over t squared times sigma 2 squared. Okay, we're just going to add this to our set of axioms. I'm not going to show you how to prove this. Okay, I don't have time for that. But essentially what this is saying is, you get a really good approximation to the top singular value by running t iterations of this algorithm. Okay, so how do we use this? We have this guarantee. How do we derive an answer for low rank approximation from this guarantee? The key step is going to be to use Pythagorean theorem. And what Pythagorean theorem will say is that if I look at any unit vector v, in our case it's going to be U tilde eventually. If I look at any unit vector v and I look at this matrix, which is A times A projected on VV transpose, then I can decompose it into the Frobenius norm of A squared minus the Frobenius norm of A VV transpose squared. And now you might look at this expression and say, like, this is not Pythagorean theorem. What are you talking about? And I'll show you that this is in just a second. Okay, and you can also do a bit of algebra to simplify this expression and show that it's actually equal to A times V, the L2 norm squared. Okay, so why is this expression Pythagorean theorem? So let's start off again with the ith row of A. Okay, so this is a vector. The projection of this vector onto this subspace, which is denoted by the vector v, is simply A times VV transpose. So this point is A times VV transpose. This length is going to be AI minus AI VV transpose, because this length is AI. And now we can apply Pythagorean theorem to this triangle. Okay, so again, this vector is AI. This vector is AI minus AI VV transpose, and this vector is AI VV transpose. And if you apply Pythagorean theorem to this, you will get an expression of this form. You sum this expression over each I, and this basically gives you the claim over here. Okay, so this is really using two things. It's using the Euclidean geometry of the Frobenius norm, and it's also using that the Frobenius norm is additive across the rows. So we can analyze it row by row, sum it up, and get this Pythagorean theorem. And this is not going to hold for non-Euclidean spaces. Okay, how do we use this Pythagorean theorem? Well, let's apply this to our vector U tilde, which was the output of this gap independent bound. Okay, so by Pythagorean theorem, we can simplify it as the Frobenius norm of A squared minus the L2 norm of A times U tilde. Okay, great. Now we have a lower bound from our gap independent analysis on this. So this gives us essentially the Frobenius norm of A squared minus the operator norm of A squared plus this additive error, which is 1 over t squared times sigma 2 squared, right? Which was the additive error over here. Okay, so if we simplify the expression over here, this is actually equal to the optimal cost. And the approximation that we're getting is this additive 1 over t squared times sigma 2 squared term. Okay, and if we set t to be 1 over root epsilon, this gives us the Bloch-Krylov guarantee from before. Okay, so this is one of the steps. This is how we analyze the part where you start off with a single vector and power it up t times. Any questions about this?
So this is just the original algorithm.
This is just the original algorithm. Now I'm going to tell you what extra stuff you have to do. Okay. So the next thing is going to be this gap dependent bound. And this bound basically says, like, if you don't want a uniform kind of guarantee, if you're okay with a bound that converges based on singular value gaps in the matrix, so this is your singular values. If the singular values have gaps, then you can converge much faster. And that's what this bound says. But more concretely, if you start off with a matrix G with B columns, you can exploit gaps between the first and the bth singular value of A. So this is how starting with a larger number of vectors to begin with, and then powering them up is helping you. Okay, more precisely, the kind of guarantee that we get is like some exponential 2 to the t times the gap here. Okay. Now, in the worst case, this gap could be unbounded. Like this gap could be like exponential in the dimension. I can cook up instances where this gap is exponential in D even. So this guarantee isn't always useful, but we're going to see how to make good use of it. Okay. So the takeaway from this slide is that if you start off with more columns, you can exploit gaps between, sigma 1 and sigma B. Okay. So what is our observation? Our main observation is that either there is a gap, a constant gap between sigma 1 and sigma B, where B is this 1 over epsilon to the 1/3, or the optimal value of the objective function has to be large. And if it's large enough, then we can get away with a less accurate solution. So there's this dichotomy going on, and we basically show how to exploit it. So let me give you a couple of examples. So consider the first case where the first singular value is 1. And by the time you get to B, which is epsilon to the 1/3, the singular value decays to 1/2. So now there's a constant gap here. If there's a constant gap, only log n iterations suffice to solve the problem. This is the gap dependent bound that I showed you last time. Okay. If it is not the case, then we know that there are at least B minus 1 singular values that are at least 1, right? Because there's no gap between, let's say all of them are 1. There's no gap between any of them. Then we know that like B minus 1 of them must be at least 1, which means that this objective value, which is the sum of squares of the singular values of from 2 to the n actually, has to be at least epsilon to the 1 over epsilon to the 1/3. Okay, so these are two example cases. I'm saying, either there's a gap and then you're done. If there's no gap, well, then the objective value has to be large as a function of epsilon.
Do the two different Krylov vectors apply in these two cases?
Exactly. I'll show you right now how. Okay, so in this case where there is a gap, this gap dependent bound like immediately gives you an answer because like there is a constant gap between sigma 1 and sigma B. So if you started off with B random vectors to begin with, you converge exponentially. So that case is easy. Now I have to show you why in this other case where there is no gap, using the first one and iterating a fewer number of times suffices. And let me try to show that. So recall the gap independent bound said if you run for t iterations, you get additive error 1 over t squared times sigma 2 squared. Sigma 2 squared is just 1. Okay, and we want this additive error to be comparable to epsilon times opt. To translate between this additive error and the optimal solution, we use Pythagoras Theorem. But take my word for it, you want this additive error to be comparable to epsilon times opt. And we just showed here that opt has to be at least 1 over epsilon to the 1/3. Okay, so it suffices to get additive error, which is epsilon to the 2/3. And then if you notice the nature of this guarantee, you can just set t to be epsilon to the 1/3 and get additive error, which is exactly what you want. So there's a bit of algebra going on here, but what is important here is that intuitively, the optimal value in this case is large, so you can get away with a less accurate solution to get get the right relative error guarantee that you want. Okay, let me pause for questions. Okay, so in the interest of time, I'm not going to spend too much time talking about how to extend this beyond Frobenius norm. But the major obstacle is, like I alluded to before, there's no Pythagorean theorem in these spaces which are not Euclidean. So what do you do there? How do you analyze, quantities of this form? The way we do it is we actually prove a one-sided Pythagorean theorem for Shannon P norms. So if there was an equality here, this would be Pythagorean theorem as we saw before for p equals 2. But what we show is this inequality for general p. And the key tool that we use to prove this inequality is a pinching inequality. Very quickly, a pinching inequality says if my matrix has block structure, so let's say my matrix A is composed of 4 block matrices, let's say A1, A2, A3, and A4, then we can relate the Shannon norm of the matrix A to the Shannon norms of the blocks by this inequality. And this is a really helpful tool in trying to analyze Shannon P norms and in fact come up with this kind of lemma, which, yeah.
Just curious, do you prove a one-sided inequality with this LED, or is the converse inequality not true?
The converse inequality is not true, and this is all we need. Yeah. No, why is it not scale invariant? If you multiply A by a fixed constant, then every single entry in this block matrix has multiplied by the same constant.
Yeah, right. And on the left, there shouldn't be a P on the right.
Oh yeah. That's right. That's a typo. Thank you. Okay, any other questions? Yeah, I'm not really getting into how we use these. Well, it's the only typo that was caught, I guess. Okay, so let me just quickly say what our lower bound instance looks like. I won't have too much time to say too much about it, but okay, so our lower bound really relies on the following really nice theorem. It says if you start off with a Wishart matrix. Now this Wishart matrix is going to be GG transpose, where this matrix G is IID Gaussian. Okay, so it's a PSD matrix. And now what is hard about this matrix is to estimate the minimum eigenvalue up to good additive error in the matrix vector model. So essentially, if you want to estimate the min eigenvalue of this matrix W, you have to read all the matrix. You have to have n matrix vector products. Okay. From this, we construct our hard instance for the lower rank approximation problem. We just set our hard instance to be I minus this Wishart matrix. And intuitively, what we show is that if you have a good approximation to the top singular value of this matrix, you can derive a good estimate to the minimum singular value of W. So that's the way our reduction works. But I don't really have time to get into this. I'm running out of time. So let me conclude with some takeaways. One key thing to notice is that we can go beyond the Chebyshev style square root speed up by exploiting more structure in the problem. So typically, it was, yeah, okay, that's all I want to say. The other takeaway is that these non-Euclidean spaces, which I didn't have too much time to get into, these are Shannon P norms for P not equals 2, have nice geometric structure. They don't have Pythagorean theorem, but they still have structure. And we can hope to exploit the structure. Okay, and then the tools that I mentioned, like the pinching inequality, can hopefully find use in other problems. Finally, the matrix vector product model is useful to prove lower bounds. and compare how well algorithms are doing, these lower bounds are unconditional as opposed to lower bounds that you could hope to prove for these problems in the RAM model. Like all of these problems are in P. In fact, they have like really fast algorithms, so it's really hard to prove lower bounds in the RAM model. This abstraction gives us a good way to prove lower bounds and compare algorithms. Okay, and finally, this question that I really like is what is the matrix vector product complexity of spectral low rank approximation? This is the P equals infinity case. We saw two algorithms that give 1 over root epsilon upper bound for this problem, and there's no unknown lower bound. So I'll leave you with this really nice question. Thanks. That's all.
So you're saying the lower bound that you obtain
Right.
does not apply to P infinity.
That's right. We have no lower bound that grows with P, as I mentioned.
You don't have any equality, Pythagorean inequality that you.
So the Pythagorean inequality we use for the upper bounds. And in the lower bounds, you have to use different tools which do not grow with P.
Okay.
Yeah. Yeah.
I'm just curious, do you, like, if you had to guess, would you think that your algorithms are optimal? You just haven't been able to show a lower bound, or do you think that better algorithms are out there for,
It's a good question. The answer could be anything. And if I had to bet on it, I'd say at least in this simple model of matrix vector products, I think 1 over root epsilon is the right answer for this. So the algorithm should be optimal. But in general, who knows? Maybe there's a better algorithm when you don't restrict yourself to this model. Yeah.
Did prior work use the matrix vector product as the kind of the basis for these analyses? That's something you guys came up with.
That's something that we use to compare algorithms. They actually give algorithms that work in RAM. So from our results, you can also get algorithms that work in RAM, and they will improve on the previous algorithms. But this gives a clear way to compare algorithms and even prove lower bounds. So you can show like exactly what algorithm is doing how well.
So that was an innovation that you guys came up with.
Right. The model isn't ours, but applying it to these problems is a contribution, you could say. The matrix vector product model is known. People have considered it before, just not for this problem.
Okay.
Once you constructed your Carlos space, are you basically allowed to do anything with those vectors?
That's right. The model, when you're proving lower bounds, you're allowed to apply any function to them. Our algorithm is, of course, bounded, like it's doing like really simple stuff. But this model, when we prove lower bounds, it allows you to apply any function to the vector that you compute.
I guess my question is related to the earlier question about like how do you find the best vector in the Carlos space?
Yeah.
And like that is effectively not like is that even relevant in this model? You can spend as much time.
Yeah. So like the algorithm that I gave you, the one that I slightly rushed to it, the explicit version of the algorithm, you can show that is the best vector in the parallel subspace.
Okay.
Yeah. And it's computable easily. Like I can go back to the algorithm if you want to see it. Where is it? Here's the algorithm. Yeah. So this vector U tilde is the best vector in the parallel subspace that you computed. And it's like fairly easy to compute. Like you compute a basis for the Krylov space, you compute this T by T matrix, and you compute its top eigen, or top singular vector. Oh, there's a question in the chat. Oh, it's not a question. Okay, are there any other questions? Okay, if not, then I can stop here. Thanks for coming.